Okay, I'm going to be describing results of a model of the Antarctic ice sheet that I've been working on a couple of years or so with my colleague Rob DeCanto. And I am going to try the first click here. For lack of time, I'm not going to try and attempt to cover the whole Cenozoic, just the Pliocene and a little bit into the future. So first I'll just give a real quick two-slide introduction to background, and then the main part of the talk is going to be presenting results of the last 5 million years through the Pliocene of our model, and to compare with a recent ANDRILL sediment core that's recently got a really good record of variations of the West Antarctic ice sheet through that time. In the last few minutes, I'll describe very recent work that I've just been doing, running the same model into the future, the next hundreds to thousands of years, see what happens, just with sensitivity experiments prescribing simple changes in the sub-ice shelf melting by the oceans. So, as an introduction, as many of you know, the ice in East Antarctica is mostly sitting on rock above, bedrock that's above sea level, the red colors here. And that makes it not in contact, physical contact with the ocean. So if the ocean warms up, it doesn't do very much, by and large, to the ice around East Antarctica. It's only vulnerable to surface melt, and even with global warming in the next few hundred years, that's projected to not be very much, and it won't cause much or hardly any retreat of East Antarctica. But West Antarctica is sitting on bedrock mostly a kilometer or more below sea level, and its large floating ice shelves in these embayments are directly in contact with the ocean, and as Ian was just talking about, the ocean can melt the ice shelves, drawing down the ice, the main part of it in the central West Antarctic. So that's the fear, the vulnerability of West Antarctica. That's been realized and examined in several prominent papers over the last 30 years, mainly theoretical, and the basis of this retreat possibility, as again Ian pointed out, this is on a larger scale, not just for little glaciers, but for the whole of West Antarctica. The concern arises because this flux across the grounding line depends really strongly on the thickness of ice there, according to this theory. So if the bed steepens upstream into this area A, the central waste, which it does, and if it begins to retreat, then you can see that that's a self-amplifying positive feedback. More and more ice will more rapidly get sucked out of the grounded interior. And the other aspect of it is, I'll just mention really briefly because Ian covered it really well, is buttressing. If ocean starts to melt the ice shelf so it floats up off its pinning points, reducing the buttressing at the grounding line, that also allows much more flux to escape, and that can initiate and enable this grounding line retreat. But to date, the time scale that this might happen is unclear. It remains unclear from this theory, and this is what I'm really going to address in this talk. Whether once it starts, this process, melting all the marine ice in West Antarctica, might take centuries or millennia, and I'm going to show model results addressing that. Okay, so the main part of the talk is the past, using the model and the paleo data to calibrate each other and have more confidence in the model. Prior to this ANDRILL core that I'm going to show, the knowledge that we had about West Antarctic collapses was really pretty spotty and indirect, mostly from observed shorelines in some of the last interglacials in the Quaternary show sea level rises above present that suggest that West Antarctic ice sheet must have collapsed at some point. But there was no continuous time series core record until this ANDRILL core. and they drilled it. ANDRILL is a big international project. This was their first core. They drilled it at the very edge of the Ross Ice Shelf here, and they drilled it a couple of years ago. They happened to get the really first really good record of ice sheet variations thought to represent the West Antarctic ice sheet through the last few million years. The question is, an important question, does this record represent just little local variations in this region, or is it representing the large-scale variations of West Antarctica? And that's, as you can imagine, that's a big concern. The ANDRILL project argues that it does represent waste, and that's certainly borne out by the model results that I'll try and quickly mention, and they do support that contention really well. So the idea is, as in the last few million years, as the grounding line has come and gone back and forth over this point, alternately depositing open ocean diatoms when it's retreated, glacial till when it's covered, when it's overridden by the ice sheet, do those correspond and go in step with the large-scale variations of West Antarctica? So here's the record itself, showing the yellow is periods of warm open ocean diatomite deposit, and the green is glacial till, cold. First of all, it's the first record that shows these really nice regular fluctuations. They're by and large 40,000, what does it say that? 40,000 year periodicity corresponding to obliquity forcing, presumably. And you can see the pattern in the early warm Pliocene is that there's much more diatom open ocean thought to represent collapsed West Antarctica, and gradually tending to more glacial conditions in the last million years of dominantly glacial. So that's the record that we're going to try and simulate and compare with our model results. And the rest of the talk is going to be this model, ice sheet model, and its results. So we use standard sets of equations for for ice flow, but a set for the sheet flow where it's grounded, and the very different scaled equations for the shelf flow extending like that where it's floating. We combined them in a new way. I don't have time to go into. And we also used recent theoretical work by Christian Schoof that parameterizes the flux at the grounding line that's acting as a boundary layer between these two very different types of flow. And Christian Schoof showed that that's really a necessary thing to put into these models to get accurate grounding line migration. And one more thing that we did to enable these long 5 million year runs is that to provide the forcings that this ice sheet model needs, we use standard parameterizations for the spatial variation, but for the long 5 million year variations of them, we assume that they're proportional to benthic delta 018 records. That's really thinking that the local variations around Antarctica are responding not to local insolation variations, say, but to global large-scale climate extending into the northern hemisphere by some mechanism that we're not specifying. And it seems to work really well, but it's a hypothesis and it needs to be tested in further work by climate models. So here is the forcing over the last 5 million years, a stacked delta 18 record running to the present. And this is one important model result, the total ice sheet volume. You can think of it as divided into 3 ranges. When the ice volume is down here low, it's corresponding to pretty much collapsed West Antarctica. All the marine ice is melted. Most of the time it was like that in the early warm Pliocene, and it becomes rare but still happens in a few of the strong interglacials in the Pleistocene. Middle range, it's always pretty much like modern, and the high values correspond to glacial extents. Happens just in the last 100,000 year world. such as it's known to have happened to this, like this at last glacial maximum, for instance. And now, this is going to be an animation just to show how it varies over the last 400,000 years of that run. The rainbow colors are ice elevation, where it's grounded, and the pink is ice thickness of the shelves, where it's floating. And I'll just try and get it running here. The first thing to notice is all the variations is mostly from West Antarctica. The East Antarctic ice sheet is remaining pretty stable. Another thing is that these collapses of West Antarctica, one's going to happen right at about 210,000 years. They're really sudden and sharp and come and go on scales of a few thousand years. And the most of the time it's glacial and modern extents. So now we're coming up to the last glacial cycle. You'll see it expand to the LGM and then retreat quickly back through the last deglaciation, and ends with a pretty good simulation of the present day. So the main motivation for this run was, this part of the project was really to compare with the ANDRILL core. And we did that by recording, in that run I just showed you, the model conditions at the closest grid point to the ANDRILL site. And we just drew here in yellow when the model said it's ice-free there, blue when there's a floating ice shelf, and green where it's covered with grounded ice. And you can compare those, we picked those colors to compare directly with the diatom and diamict glacial till colors in the core. And you can, if you're kind and you squint your eyes, you can say that it's a reasonable match in the bigger aspects of it, the general trend. These don't match at all. They're just strange. They're not explained by this model, why they're there in the glacial in the early Pliocene. But apart from that, there's a pretty good match. Okay, so now to the future and the last part of the talk. I haven't shown you a couple of other things we compared and validated the model with, the data on the last deglaciation, for instance. But I can claim at least that we've done a reasonable job at validating this model, doing the best we can, fitting it to what's known about past variations of West Antarctica. So now the natural thing to do is just to run it a little bit into the future. But we have to do something about the forcing parameterization. The one we used for the last 5 million years is not applicable at all to the, this unique anthropogenic pulse of CO2 that we're doing. And that's going to need, of course, climate models, ocean models to couple with ice sheet models. And that's going to happen in the future, but I haven't done that at all. Here, just really doing a sensitivity test with arbitrary increases in the ocean, sub-ice ocean melt rate. And that's the reason I picked that and not snowfall or something, is that's the dominant forcing in the model for retreats of the ice sheet. So that's what I'm going to do. And this slide is just to point out that the future variations of the melting by the ocean under the ice shelves is a really hard and tricky problem. It depends on changes in the circulation, not just warming of the ocean. Oceanographers are beginning to attack this actively, but there's nothing really available in detail that we can use available yet, just orders of magnitudes, sort of back of the envelope numbers that what it might increase to. And that's what I've done. In our simple parameterization, we describe sub-ice ocean melt at any time by a triplet of 3 numbers, but the first one is the most important. That's the one that's the average over pretty much all of the large ice shelves, sorry. And the modern one we have is 0.1 meters per year of the rate of the melt going up under the ice shelf. And in these experiments I'm going to show, just increased it to 2 based on these preliminary oceanographic results, 2 meters per year. And the other experiment I'll show is an extreme experiment where we remove all the ice shelves. And that's indicated by infinity, increasing the melt rate to infinity. Okay. So, and also, mainly I'm going to use a nested grid over West Antarctica to get down to 10 kilometers, and that resolves the ice streams better, as I'll show in an animation. So the first, the first animation I'll show is the extreme extreme experiment, removing all ice shelves instantaneously, starting with the modern. So you see the first time step, all the ice shelves go away, and as we run it, it very quickly collapses. This is really kind of scary in this extreme scenario. Within 300 years, all of this grounded ice has drained away, and all that's left is the high ice sitting on land that's above sea level in 300 years. So now I'm going to show a similar view, but now it's in 3D, and it's for the experiment with increasing it to a perhaps more reasonable, for the next few hundred years, 2 meters a year over the ice shelves. And this is showing ice speeds, ice surface speeds, to also at the same time give you an idea of the dynamics of the ice sheet model as it runs along. You'll see these ice streams fluctuating. These flat areas are the ice shelves, and here we go. So you see much the same retreat. It's happening slower though, right? It's now at 600 years, still going. You'll see an inlet, a tongue extend out from the Ross grounding line about now there, and it'll hook up with the Thwaites drainage, and then a little later everything forms a central seaway. And at the end, the dwindling ice supply lets the ice shelves totally melt. So we get pretty much the same retreat, but it takes an order of magnitude longer with the slower retreat. Here's the sea level rise from those same experiments. Red is the quick instantaneous retreat, and blue is the 2 meters a year increase. And if I should have run this longer, they match up, they go to the same thing after about 4,000 years with 3 meters ice sea level rise. The difference between these is, in terms of the rates, especially at the beginning, is really huge. The instantaneous removal of ice shelves produces meters of sea level rise per century at the beginning, compared with 10 to 20 centimeters with 2 meters per year melt. So the difference between those is, of course, really important, and we're going to need detailed ocean models and coupled ice sheet climate models to distinguish between the two. So I think I'll skip to the end here. Yeah. I'll mention, this is something I'll skip over, but I mention it in one bullet here. So the summary is, just for this study, emphatically saying this is just one study. It should be and will be, I'm sure, tested by models coming along and other models in the next few years. At least in this model, with any plausible, reasonable increase in sub-ice ocean melt, that causes wastes to collapse. And then the thing I skipped over is, of course, snowfall will also increase, and that can change the net sea level effect by storing snow on East Antarctica significantly, but waste always collapses no matter what you do. The time scale, as I described, depends on the magnitude and also the placement, whether it occurs in Pine Island or the bigger ice shelves. And to really see what's going on and make scenarios and projections, we'll need other regional ocean models, global climate models. Okay. And I have a whole long list of uncertainties. I'll just mention the two of them. This model does have some of the new physics that people want to have in ice sheet models to improve on the AR4 projections, some of it. Ice streams, grounding line physics, but It's still kind of a hybrid heuristic way of doing it, and this will be, I'm sure, tested in this next generation set of ice sheet models that are coming along, massively parallel, high resolution, in the next 2 or 3 years by other groups. And we also need, one thing I want to do is test it against a recent observed beginning of the retreat in the Pine Island Thwaites glacier regions that are already beginning to retreat. And now there's a few other aspects of the new physics that Ian described quite a bit. Basal hydrology, moulins, lubricating the bed is not in this model at all, and a couple of other things. And their effect on these results is uncertain and remains to be investigated. And I'll stop there. Thank you.
Time for one question. Looked at the ANDRILL record. In the very early part, there were those substantial glacial expansions which are not shown in your model. Can you speculate what was different at that time, or what is not included in the model?
Yes, no, I don't have any idea. I've talked to them and don't know.
Okay, this is well outside my field, so it might be a naive question, but when you were running your model through the past, what caught my eye was that as the West Antarctic ice sheet shrank, the eastern one seemed to build up. Am I right about that? Is that, it seemed to get thicker or more red, I saw it there.
Yes, I think that's, I mean, that's probably true. It's certainly true in the last glacial cycles.
Okay.
And that's because as the ocean gets warmer and attacks Western Antarctica, in Eastern Antarctica, the snowfall is increasing somewhat by just the warmer air and more snowfall. So it builds up ice in its center and gets higher.
So for somebody who doesn't work as this may be a question for others in the audience, but what would be the impact on the delta 18O temperature relation if you're opening up the ocean and perhaps transporting moisture more rapidly or with less rain out or whatever processes go on? Is there some implications there?
I guess I don't, well, maybe others can answer better, but there'd be a sort of trade-off, and I don't know what the net effect is, but we can put delta O18. Another thing I want to do in the future is put in delta O18 as a tracer in the ice sheet model and explicitly model the net effect.